Acceleration, gravity, and frames of reference. Here are your priming questions. Now, for acceleration, this goes back to the last presentation. Acceleration is the change in velocity over time. So delta v over delta t. So the change in velocity over time, that's the acceleration. Now, what's interesting about this is that this can be a change in speed and or a change in direction. So speed and or direction. What we need to remember is that acceleration and velocity are both vector quantities. So if we change the direction, we change the velocity vector. If you have a change in velocity over time, you have an acceleration. An easy example for this would be if you have the same speed but you're rounding a corner or going through a curve, your speed will remain the same, but your direction will be changing. So that means you have an acceleration even though you have the same speed. Now, if you have a different speed, that's much easier to see as an acceleration. Now, gravity, we're going to keep a simple definition for right now. Gravity is an attractive force that can cause an acceleration. Now, I say can because, depending on how the object is located, it may or may not cause that particular acceleration. It will always have a force, though. So let's say, for example, that you are holding an apple, and you decide to let go of this apple, and you notice that the apple falls. This is due to gravity. This apple is actually being attracted to the center of the earth. It's just that the ground blocks it. If we had a big hole that went all the way to the center of the earth, this apple would bounce around until it settled in the center of the earth, if that were possible. Now, what's also interesting to note is the apple is also attracting the earth, but we'll talk more about that later. This idea of gravity is also what keeps us on the ground, and so that we're not floating up somewhere in the air. This is also what allows us to sit. And in this case, you can feel the chair pushing back up on you. If we had no chair, you would just simply fall to the ground, but the chair pushes back up. This is where what we mean by it can cause an acceleration, but if something is in the way, that something will be applying a force back up to you. Frames of reference. Okay, so we need to be thinking about exactly who is moving and how fast. This depends on your frame of reference. For example, let's say we have an airplane and it's moving to the right at, we'll go and say 250 meters per second. Now, if we are an observer, like this guy down here, watching this airplane, it appears to us that this airplane is moving to the right at 250 meters per second. But if we are inside of the plane, when you're inside of the plane does not appear to be moving 250 meters per second. Outside actually seems to be moving 250 meters per second backwards. You don't have a right or a left in that particular case when you're in the airplane. And so depending on where you're at, you can have a different frame of reference. Now, inside of this airplane, most of you will have the same frame of reference, but outside of the airplane, you'll have a very different frame of reference. And we can keep going to a bigger and bigger scale in this case. If we consider a person that is simply just standing on the ground, if our frame of reference is in relation to the center of the earth or to one of the poles in this case, we just standing on the earth will actually appear to be moving very, very quickly. We go to an even larger scale. If we use the sun as our frame of reference, not only are we rotating around the earth, but we are also orbiting around the sun, and we are going even faster. And then if we were to go to an even larger scale, the universal scale, I guess you can think of it like that, or a galaxy scale, you can see that we are going to be moving or rotating within a galaxy. And if you look at multiple galaxies, you can see that they will be moving away from each other, and our galaxy is actually expanding at this point. So depending on what your frame of reference is, will determine what you consider to be the velocity, whether something is moving or not. And so you always need to take that into account. Now, inertial frame of reference. For this, for any problem, we need to establish the inertial frame of reference. This is just another term that we use for frame of reference. Inertial is just a descriptor that we use. Now, for this, we need to establish the origin. Okay, and what this means is where we are measuring from. So we can set it however we like. We don't all have to use the same exact 0 or origin, we can all use different ones, but our answers should be comparable. Once we establish our 0 point, then we need to establish the positive direction or directions if we're working in more than one dimension. So for example, for the most of the problems, we will be using up and to the right as our positive. Or we can say north and east. There are different ways to say this. But for some problems, in particular the problems that we use with gravity or free fall problems where the object is only moving down, it is more convenient to select down as positive. And when you do something like this, that automatically means that up is negative. And so we can set our positive and negative directions however we like. Now, depending on the problem, you might get a positive or negative answer. And so when we are giving our answers, we typically don't want to use just positive or negative. We want to use the magnitude, which will be a positive value, even if we get a negative value. So it'll just be the magnitude or the size of the value and the direction. So rather than saying, if we had set this as our frame of reference, rather than saying negative 2.9 meters, which would actually be up, we would want to say 2.9 meters up. So we have our magnitude and we have our direction separate. This is going to be a lot easier to understand and easier to work with, especially when you're working with multiple people. And here are your priming questions again.